Sometimes we can't find an exact solution to a given an explicit formula for the initial value problem, but we can often use a computer to generate a table approximate of numerical value for y for a value of x in an appropriate interval. Such table is called a numerical solution of the problem, and the method in which we generate the table is called a numerical method. The most popular method that we use is called the Euler method. Given y prime equal to f of xy and y equal x naught y naught, we can approximate the solution using the linearization L of x equal y of x naught plus y prime of x naught times x minus x naught, or the same equivalent of the equation is L of x equal y naught plus f of x naught y naught, because we are given the differential equation times x minus x naught. The function L of x is a good approximation to y of x in a short interval about x naught. So if we make various short interval, then we can connect kind of a curve. We can connect a curve, maybe a pretty choppy curve, but it will be a good approximation of the actual solution. The basis of Euler method to pack together a string of linearization. Okay, so recall that we have earlier that L of x1, we call that L of x1 is equal to y naught plus f of x naught y naught times x minus x naught, right? Now the distance of x minus x naught is just delta x move from one point to the other. Now we have the first piece of the function, this first piece here. Okay, so the second piece here will be calculated based on the approximation, based on the linearization of the 2 point x1, y1, x2, y2. So the second curve, linearization x2, is equal to y1 plus f of x1, y1 times delta x. Similarly, L3 x of x3 is equal to y2 plus f of x2 y2 times delta x. Now notice that we can string a curve together. But there will be some error of approximation. Okay, so the error is found by taking the difference between the value of the curve and the actual value of the solution curve. Consider the initial value problem y prime equal f of xy and y of x naught equal y naught. To approximate solution to this problem using Euler method, we define xn equal x naught plus nh. So h is actually just the same. So h is equal to delta x. So the difference between 2 points. Then yn equal y of n minus 1 plus h times f of x n minus 1 y n minus 1, where h greater than 0 represents the step sign and n is an integer starting with 1. Okay. The number of steps taken is counted by the variable n. So find the first 3 approximations using Euler methods for the initial value problem, starting with x naught equals 0 and delta dx equals 0.1. So dx equals 0.1 is the same as delta x. Okay, so the first step, well, y naught equal to 1. Well, we know that x naught equals 0. This meant that y naught is equal to 1, and that we were told delta x equals 0.1. So I can write my equation y1 is equal to 1 plus 0.1 times 1 plus 1, that equal to 1.2. The step 2, x1 now equal to x naught plus 0.1, that equal to 0.1. And y1 now equal to 1.2. So y2 is equal to 1.2 plus 0.1 times 1 plus 1.2, that is 1.42. So now we have x2 equals 0.2 and y2 equal to 1.42 we calculate in the previous step. So now we can calculate with y3. Well, y3 is equal to 1.42 plus 0.1 times 1 plus 1.42. This is 1.662. Okay. Now let's say if I want to do 10 approximation. I'm not going to do this by hand because it would take way too long. It's ridiculous, right? So let's see how do we do this using Excel. Let's take a look at the next question. Use Euler method to solve y prime equal 1 plus y, where y naught equal 1. On the interval 0 to 1, starting at x naught equals 0, and taking the step dx equals 0.1. Okay, so that we did the first 3 steps earlier. And then we will repeat with d equals 0.05. Then we will compare the approximation with the actual value of the solution. I'll go ahead and start with Excel. We make this calculation. We start with x naught equals 0, y1 equal y of 0 equal 1. Okay. Well, in the next value, y1 equal to 1, x1 then will be equal to the y naught plus 0.1. And we continue until we get to 1. So the first value that will be calculated is y1. What the y1 then equal to y naught, and we want this value y naught to stay equal to y naught, and we add with 0.1, that is dx, right? Multiply with 1 plus y naught. So that is our first value at 1.2. Well, then in our next value in our table, we use y being y1, that is equal 1.2, and the formula is the same. Let's see what had changed. Oh, d5, and we don't use d5. So here we use the value for y here is equal to the approximation here, and this is equal to y2. Okay, so now if I can just continue writing this down, the formula don't change, you would see that these are the approximation of the value of that of that function y prime equal 1 plus y. Now let's compare that to the exact solution, the y exact solution. The solution curve of this was 2e to the x minus 1. Okay. So let's calculate these. So what happened here? So equal 2 times exponent exponent 1 minus 1. Oh, this should be exponent. So D4 should be changed to C4 because that is our x value. Okay. So now here's our exact value. And what is the error? The error is equal to the exact value minus the estimation. So we have a very close curve, right? So let's go ahead and I will copy this into our page. Now let's see what happened when we reevaluate this with d equal to 0.05. So let's change this value, d equals 0.05. The formula is all the same. So if d equals 0.05, we're still starting out at 0. Okay, then we continue this. And let's make sure that our formula still continue the same. So we need to change this delta. Now after we change it, we don't need this row. And what are we adding? 0.05 for delta, okay. Let's continue until we get to 1. And I can continue all this. And make sure that I change everything to 0.05 for the D. Okay. So now we can see that here we have a closer estimation. So the closer the step is, the closer the dx, the closer our approximation to the exact value. Okay, I'll put this over to our page. So like I said, Euler method can be used to approximate the curve pretty closely to what the actual curve is. Because if you look at the error, the estimation and the exact curve is not much of a difference. Okay. And again, we won't ever have to do this by hand. We always want to have to use this with Excel or with a graphing calculator. Okay.